In Lesson 4 of Abstract Algebra, I explain the algebraic structures that carry the names vector space and algebra. In particular, a vector space results from the pairing of a division ring structure on a set K and an abelian group structure on another set V. The set K is called the ring of scalars, and the set V the set of vectors. An algebra results from the pairing of a ring with identity structure in K with a ring structure in V. Also in Lesson 4, I commented that quite often the ring of scalars is a field. And although I bypassed this comment quite fast, it is not as trivial as you might think. Every time a property is added in a structure, the structure gets tighter since lots of new relations among the elements are created. Therefore, this video aims to persuade you to place extra attention to the properties adopted for a vector space and an algebra in each book. There are minor differences, but they result to big consequences. Before I continue, let me introduce a simplification in my notation, as it is quite common in all books. I will denote both addition of scalars and addition of vectors by the familiar plus sign. It is always clear from the context which addition the sign indicates. Similarly, I will indicate by juxtaposition or by a dot the product of two scalars and the product of a scalar with a vector. It is always clear from the context which type of product is meant. In the definition of a vector space that I presented in Lesson 4, the set of vectors equipped with an additive operation was required to be an abelian group. The vectors can be scaled by the elements of another set K, which is equipped with addition and multiplication such that a division ring structure on K is established. Scaling means that there exists a function from the Cartesian product K times V to V, known as scalar multiplication. Finally, scalar multiplication is required to satisfy four compatibility equations. Looking at these compatibility equations, we can interpret the first two as distributive laws for the scalar multiplication, the third equation as the associative law for the scalar multiplication, and the fourth equation as the promotion of a unit element of the division ring to a unit element for the scalar multiplication. Moving from the definition of a vector space to the definition of an algebra, a second operation must be defined on V such that V equipped with the two operations becomes a ring. For the scalars of an algebra, in Lesson 4, I had adopted the convention that the set of scalars equipped with the operations of addition and multiplication is a ring with identity. In most applications, though, we wish to scale vectors up and down. So let's allow multiplicative inverses and promote it again to a division ring. For the algebra, the introduction of the multiplicative operation in V introduces also a new compatibility equation between this operation and scalar multiplication, which can be interpreted as associativity. It is important to note here that, other than the requirement of the ring structure in the set of vectors and the fifth compatibility equation, no other requirement is placed on the multiplicative operation between vectors. Finally, recall that a division ring only lacks commutativity of the multiplicative operation to become a field. If commutativity is added, then the compatibility equation 3 becomes two equations. We say that a function f is linear if, for all scalars lambda and mi, and all vectors u and v, the following equality is true. In the previous definition, I have assumed that the domain of the function f is the set of vectors v. However, a linear function can be defined with domain the set of scalars k. After all, the two sets k and v can be equal. The requirement of linearity may also be written as two equations in the following form. If a function of two variables is given and it is linear in each of its arguments, we call it bilinear. I have claimed that the compatibility conditions for a vector space and an algebra can be interpreted as distributive, associative, and identity laws. However, we can see them in another way. Let's restore the function notation for the scalar multiplication and indicate it by s. Using this function, the functional form of the compatibility equations for a vector space are as follows. Then notice that the second and third compatibility conditions imply that the scalar multiplication is a linear function with respect to the scalar argument. The first compatibility condition is half the linearity for the vectorial argument. The other half requirement for linearity fails since the set of scalars is a division algebra and not a field. Let's see this explicitly. Let's look at the third compatibility equation again. Lacking commutativity for the multiplication of the scalars, the right-hand side cannot be rewritten in the form which is required for linearity. But if we promote the set of scalars k from a division algebra to a field, then the scalar multiplication becomes a bilinear operation. In this case, we call the vector space a linear space. This terminology is not very popular these days. Unfortunately, the term vector space is used in all instances, which makes things slightly confusing for beginning learners. To advance from a linear space to a linear algebra, we equip the set of vectors with a multiplicative operation to promote it to a ring. I will indicate the binary operation between vectors as a function p. At the same time, we add the fifth compatibility equation, which in functional form is written as. Notice that this compatibility equation gives two of the four equations needed for declaring the multiplicative operation between vectors a bilinear operation. Well, there is nothing to stop us from introducing a bilinear multiplicative operation in V. In this case, the resulting algebra is called linear algebra. The most common multiplicative bilinear operations for linear algebras are 1. The standard Cayley product of matrices. All standard textbooks entitled Linear Algebra study the algebra of matrices based on this operation. 2. The commutator of two matrices. The resulting algebra belongs to the so-called Lie algebras. Lie algebras underlie all physics. 3. The anticommutator of two matrices. The resulting algebra belongs to the so-called Jordan algebras. 4. The cross product of three-dimensional vectors. The resulting algebra is the familiar algebra of three-dimensional vectors used by students early on their math and physics studies without even paying attention to the underlying structure. Recall that often mathematicians allow a ring to be non-associative. This is the case with some of the previous operations. I will discuss non-associative algebras in a future video. Now you know what the adjective linear stands for in linear algebra, and I have finished my presentation. I hope you liked it. If you did, please subscribe to my channel to help the creation of more videos. Thanks a lot for your support.